All right. Let's get going. Juan, you're a few days early for Halloween.
Yeah, it's the last week, and I wanted to spread some Halloween joy real quick. I got 2 other costumes for Wednesday and Friday.
I see. Okay, for those who are thinking of taking me up in the alternative grading agreement, please send me that agreement form sometime today, and then start doing the alternative assignments posted on Blackboard. You don't have to turn in the regular assignments starting this week. Last time we were going over various identities satisfied by Fourier transforms. I'd like to talk about one more. It turns out that there is a generalization of Parseval's theorem. Remember that Parseval's theorem said that we could take a Fourier series and compute the square integral of the function by summing over Fourier coefficients. For a periodic function, the integral over one full period was equal to a naught squared over 4 plus 1/2 sum over all the coefficients of this. And the reason why we cared about that is because oftentimes we're talking about waves or other oscillating phenomena for which the energy is proportional to the square of the function, it's proportional to the square of a field or the square of a displacement of a spring or whatever it may be. And so computing the integral of the squared function is very physically meaningful. Well, just as we can use Fourier series to compute or to model periodic waves, we can use Fourier transforms to model non-periodic phenomena. And there is a generalization there too. For a non-periodic function with a Fourier transform that exists, i.e. our integrals converge, we can compute the integral from minus infinity to infinity of f star of t, f of t. That would just be a fancy way of writing out the absolute value squared. And there is a very simple identity for that too, which means that we can calculate the energy in terms of a Fourier transform rather than having to take the Fourier transform, which is representing your function as something that depends on omega or k or whatever you're calling your frequency. We won't have to transform back to a function of t or x or whatever you're calling your variable. We can just work with omega and k the whole way through. Let's see how that would work. That would be the integral from t equals 0 to, sorry, from t equals minus infinity, my bad, minus infinity to infinity. And then we're going to represent one of these as a function of omega. So we're going to stick with f star of t here, but I'm going to write the other one as a function of omega. So that's going to be the integral from omega equals minus infinity to infinity of a of omega e to the I omega t. All right, and this is just a fancy way of writing out f of t in terms of our Fourier transform. Any questions on how or why I wrote it that way?
Yes, but I'm assuming you're going to tell us why.
You mean why in terms of the bigger motivation, or why in terms of why is this a valid way to write f of t?
The motivation.
Oh, I just gave the bigger motivation a minute ago, that we want to be able to calculate the energy by only working with with the amplitude as a function of omega, instead of having to work with the, we want to just be able to work with things in terms of omega the whole way through.
Right. Okay. Got it.
Okay. Well, we can swap around the order of integration. We've got a double integral. We can rewrite this double integral as the integral from t equals minus infinity to infinity. Actually, sorry, I said I'm going to swap the order of integration. Omega equals minus infinity to infinity. The integral of t from t equals minus infinity to infinity. And I'm going to put a of omega here. I'm going to put f star of t e to the I omega t dt d omega. So I've just swapped around the order of the integrals, which we're allowed to do for double integrals. Now, the thing I've just circled, what does that look like?
The inverse Fourier transform?
No, it looks like an inverse Fourier transform, and it has e to the I omega t. But since we're not integrating over omega, which is how we normally think of an inverse Fourier transform, what else does it look like?
The conjugate of A?
Yep, this is a star. Because remember, a of omega would be, I'll use a thicker font for that. A of omega would be the integral of f of t e to the minus I omega t dt. And so a star would just be the integral of f star of t e to the plus I omega t dt. So what I've got here is the integral from minus infinity to infinity of a of omega, a star of omega, d omega is also equal to the integral from minus infinity to infinity of f of t, f star of t, dt. Questions?
I'm just a little iffy when you, like in the beginning, we started off with one integral and then you, I guess, divided them or separated them, and now we have two integrals. Is that just a property of integrals that I'm forgetting?
Well, we started with this integral.
Mm-hmm.
And then I decided, well, f of t, this is most certainly f of t. Okay? This is t. I can replace, in any equation, I can replace something with another thing that's exactly equal to it. All right? Just like I could replace a function with its Taylor series, if that Taylor series exists and converges within the range that we're working over. I could replace a function with something, with some sort of identity. Like I can replace a polynomial with the product of factors. All right, if I had, x squared plus 4x plus 4, I could replace that with x plus 2 squared. That would be valid. All right, And you're used to that. It's something that you're used to. But the basic idea there was just that I'm replacing something with another thing that's equal to it. So here I had f of t, and I replace it with this integral because that's what f of t is. That is absolutely equal to f of t.
Okay, thank you.
And I'm replacing it with something more complicated. I'm taking the more complicated intermediate step to get back to the thing that I really want. It's like taking something apart, making a change, and then putting it back together again, or taking something apart to make a modification, to use some other property of it, okay? It's like doing surgery. You take the person apart, you decide to make some changes, you put it back together, you still have a person, hopefully a better person, a healthy, but you still have, you're taking it apart and then putting it back together again. So all I did here was say, look, this f of t could be written as this integral. So let's replace it with this integral. Now we've got a double integral. It looks messy. It looks like I've made things worse rather than better. But I can swap the order of the double integral, and I see that it's also equal to something else. And this is a of omega. And the reason why we want to do it this way is that, look, in any class you've taken on waves or optics, you've probably spent a lot of time working with plane waves, writing out waves as e to the I kx minus omega t. All right, those things are easier to work with than a lot of the alternative ways that you could work with waves. There are other ways to work with waves, but virtually every optics and acoustics and quantum mechanics textbook works with waves in that form. It's just easier to work with the e to the I omega t representation of a wave, or the e to the I kx omega t representation of a wave. We want to be able to take a wave, break it into these pieces, these e to the I kx minus omega t's, and then work with those. And the Fourier transform is just a way of saying that we can write any wave as a sum over of all of those, as a superposition of all of those. And anything that we would normally do by integrating over time, if we were to switch notation, we could have just as easily written integral of f of x, f star of x dx is equal to the integral of a of k, a star of k, dk. Whichever way I choose to work with things, they're both valid. You're going to use this all the time next year in quantum mechanics when they talk about the position basis and the momentum basis, all right, that you can write things in more than one way. Another way of thinking about it is it's like saying that if I have two pairs of axes, here's my x and y axis, here's my x prime, y prime axis, and here's my vector v. The length of v squared is equal to vx squared plus vy squared. But it's also equal to vx prime squared plus vy prime squared. This is two different ways of writing out v. V is the same object. It has the same length, the same direction. I can either write it in terms of the x and y axes or the x prime and y prime axes. And either way, the squared length, which we care about for reasons like, say, computing a kinetic energy or computing a squared electric field to find an energy density, that square length can be written as the sum of squares of components, either in this coordinate system, x, y, or this coordinate system, x prime, y prime. Those are both valid ways to write it. They both give the same result. And the equation takes the same form in both, so that we don't really have to change things when we switch from one representation to another. And that's all that Parseval's theorem is saying here, because you can think of a function as an infinite dimensional vector. I've been telling you all semester that our ultimate goal is to take functions that represent things in physics like electric fields or quantum mechanical waves and break those functions up into little pieces. And that's all we've been doing. Taylor series, that's one way of breaking a function into a piece. Fourier series, that's another way of breaking a function into a piece. Well, here, this is really an infinite dimensional basis, okay? We're representing a function either by telling you its value at every single input x, which is an infinite number of things. It's a very tedious way to do it if you really think about it, or by telling you the amplitude of a wave with every single possible k, adding up an infinite number of waves, all of them with different k's or omegas, depending on what notation we're using, adding up an infinite number of waves with different frequencies. And I could specify my function either way, via an infinite number of values at an infinite number of x's, or an infinite number of waves, each with its own amplitude. So I have an infinite list of amplitudes. And either way, I want to ultimately integrate my squared function. The formula is the same, whether I'm working with frequencies or times. Other questions? Going once, going twice. I don't remember whether I made this analogy last week. I know I made it in office hours. I don't remember if I made it in class for everyone. So I'll say it again. Another way to think about why we're breaking up functions in all of these different ways, Fourier transforms, Taylor series, Fourier series. We've done a little bit with Legendre polynomials, and we're going to do more in a few weeks. Think about the question, what is this substance made out of? Well, there are lots of ways to answer the question, what is this physical substance made out of? One way to answer that question would be electrons, protons, and neutrons. And unless you're doing some very exotic experiment in particle physics, or you're talking about some very extreme conditions in astrophysics, or you're talking about dark matter. But other than those situations, the answer electrons, protons, and neutrons would almost always be valid. It might also be useless because everything's made out of electrons, protons, and neutrons. But sometimes that would be the right way to analyze it. Other times the answer would be, well, it's made out of these elements. It's got some carbon, it's got some hydrogen, it's got some oxygen, it's got a little bit of sulfur, whatever. That would be a very valid way of answering a question. Oftentimes that would be the answer that the chemist would need to know. What are the elements in it? Except if you're talking about biology, just about every substance in biology has carbon, hydrogen, oxygen, some nitrogen, and then small amounts of sulfur, phosphorus, magnesium, calcium, and a few other things. So saying, it's mostly carbon, hydrogen, nitrogen, and oxygen would only get you so far. So a biologist might want to know, well, is this made out of amino acids? Is this made out of lipids or fats? Is this made out of carbohydrates? Is this made out of nucleic acids, i.e. DNA or RNA? Sometimes that would be the right question to ask. But all of these would be valid. All of these would be accurate answers to the question, what is this thing made out of? Electrons, protons, and neutrons, or elements, or amino acids. Somebody might say, well, of course it's a protein. I know it's made out of amino acids. What I want to know is it made out of hydrophobic amino acids because it's sitting in a lipid bilayer, or is it made out of hydrophilic amino acids because it's in an aqueous environment? And again, that would just be another way of breaking it down. Well, likewise in physics, sometimes we just simply write down any arbitrary formula for a function. Break it up into x and x squared and x cubed and x to the fourth in the Taylor series. And other times we break it up into oscillating functions with either a Fourier series or Fourier transform. And sometimes we break it up into special polynomials with Legendre polynomials. Or sometimes we break it up into spherical or circular waves via Bessel functions, which we're going to get to later this semester. That's the motivation for a lot of this. Any other questions before we move on to a new topic? Okay, much of what we're going to do for the remainder of today's lecture is really, this one goes out to the experimentalists in the house, all right? This one goes out to all of you experimentalists, because even though it's going to seem very mathematical, this is all about the nuts and bolts of modeling experimental data. So let's talk about convolution integrals. Let's start off by thinking of the simplest yet most unachievable experiment in the world. One where you have a perfectly pure input to your experiment. Maybe that means that you shine a perfectly pure beam of light into an apparatus. Maybe it means that you've got something producing the purest musical note ever. Maybe it means that you have an absolutely pure substance. Maybe it means that you have a perfectly flat current that doesn't waver or jiggle, that has no noise. But whatever it is, you've got the purest input imaginable to your device, okay? And your device is breaking it up into a spectrum with, to tell you how much of the input has this value of a parameter I'm going to call lambda, which is often a wavelength. It's often a spectrometer. You're often shining light into something. And people in every branch of physics shine light into spectrometers. It's not just optical physicists. Material scientists and solid state physicists shine light into things because materials emit light and they can use that to figure out what's going on in the material. Biophysicists use light all the time to look inside of living things. Astronomers send light into spectrometers to find out what is the spectrum of light that's coming from a star or a planet or whatever. So we're sending a signal into a device. If you want to think about it as a spectrometer, think about it that way. It would be a very useful and valid way to think about it. So we have a pure input. And if our device was perfect, then what you would see on the screen is one very sharp line saying that 100% of our signal is at lambda 1. 100% of our input is what I should say.
Professor, I gotta ask. So are you going to say that eventually the more convoluted a signal is, the wider the width of the function is going to be?
Yes, but we need to be a little bit careful with the word convoluted. Convolution has a very precise mathematical meaning. Not every bit of algebraic tediousness that gives you something that complicated is a convolution integral, but yes.
Okay.
So if we had a pure input and we said that this vertical axis is like some sort of amount. I'm going to start with the notation of the Fourier Transform book, even though I hate this notation, and then I'm going to relax from it. What they say is they call the vertical axis O, meaning output. And I understand why they do that. The problem is that while printers can make a very clear distinction between O, the letter, and 0, the number, human beings writing with their fingers almost never do. But what they say is that the integral of O output d lambda equals 1, meaning that that 100% of the output was that the amount of output adds up to 100%. But in fact, this is not an output. What I've just drawn in blue is not an output. This is a source, S of lambda, right? And it's true that the integral of S of lambda d lambda equals 1. But what we really measure is something that's going to look like that. The signal gets spread out. You're never going to get a perfectly pure output. You work with any realistic spectrometer, and actually, if the spectrometer is good, it's going to give you a finite line width. Now you may be thinking, wait a minute, what do you mean if my spectrometer is good? If it's bad, it will give me a finite line width. If it's good, it'll give me something pure. Well, in practice, if it's bad or if it's badly programmed, what that means is that it's dividing the data up into such coarse chunks that you're not seeing just how much the stuff was actually spread out. There's always some chain of events inside your device. Light or sound or whatever stuff comes in, then it goes through various instruments. If it's light, it's going through a grating, it's spreading out, it's diffracting. If you were doing something like mass spectrometers, where you're taking a substance and then vaporizing it and then measuring the mass of each molecule or chunk that comes out, essentially apply some sort of force and see how much the stuff accelerates. And so different molecules or chunks will wind up in different places. And if you measure really coarsely, maybe you say, hey, they all went to the same place. That just means that you weren't actually able to measure the spread. But if you were actually able to measure the spread and see what's really going on in there, there would be a spread. So if your instrument is good enough to tell you about its own limitations, then you will not see a pure output. If your instrument is bad, it won't even know its own limits, and you will just see a pure spike. It's a little bit of the Dunning-Kruger effect. Your instrument should know its own limitations. If it's really good, it does. Okay, so that's the idea of an instrument. Any questions before we go on to a slightly more complicated input and output?
What do you have written down on the y-axis?
Amount.
Amount. Thank you.
But the book insists on saying O for output, and there's no way that could possibly go wrong. It reminds me of something in optics textbooks where some people will say 1 over the object distance plus 1 over the image distance is 1 over the focal length. And we're just supposed to know that that's not 1 over 0 plus 1 over I. And honestly, I'm always saying you should be able to figure out some equations from context. Written out like this, yeah, I agree. You should know it's not 1 over 0 plus 1 over the square root of -1. The problem is that then people take this equation and they start manipulating it and plugging those distances in for other things. And pretty soon you've got O and or I in lots of other places where it's not at all clear that what you're dealing with is the thin lens equation. So I hate any notation that uses O as a variable. But this textbook author thought would be lovely. One other thing. In this case, our source, S of lambda, we could write it as delta of lambda minus lambda 1. Because, you know, it's got a huge, huge spike. And if we integrate, we find that the area under the curve adds up to 1, which just means that we've accounted for 100% of the source. Now, let's go to something still close to ideal. Now we've got 2 sources, lambda 1, lambda 2. Output O. And ideally, they look like this. Maybe they have different heights, which I'm going to call A1 and A2. But I wind up getting 2 broad peaks. And here's the problem. The problem is that no real instrument will ever be able to say, hey, you know what's going on right here? What's going on right here is actually the sum of this and this. No real instrument knows how to do that. Instead, it's just going to say, hey, I've got a signal right there. No real instrument is going to say, hey, I've got two things of this height. It's just going to say, I've got one thing of that height. And no real instrument knows how to say, I've got a faint thing here plus a big thing here. All it knows is that. So what I really get is something that looks like this. The pink instead, the purplish pink instead of the red. All right. So I've got two overlapping peaks. All right. That's what happens in any real instrument. It happens in any real optical spectrometer, any real infrared spectrometer, any real X-ray spectrometer, any real mass spectrometer, any real anything spectrometer. I get two peaks that overlap. And you could look at these things and still more or less figure out where the peaks are supposed to be. And these are just still far enough away that, you know, we can measure the heights pretty accurately. This height actually does get pushed up a little bit. And this height actually does get pushed up a little bit, but still you can measure pretty accurately. But you see how everything's starting to get a little more complicated? You can't measure the peaks with perfect precision anymore. All right, that is the real problem. And that is, in some sense, the real problem in all of experimental physics. If your two signals are clearly distinct, then we don't have to worry about this. If your two signals are clearly distinct, then even a university administrator could measure it. They probably wouldn't. They'd probably issue some edict that screws it up anyway, but they could at least try. Yeah. Believe me, there are stories I can't tell right now, but in any but the thing is that all of the easy signals have been measured. All of the easy signals get done very quickly. Then someone says, I want to start looking at the details. I want to start looking at the hard parts. And every branch of physics very quickly runs up against this problem. In some sense, this is the problem of experimental physics. The other problem of, well, it's not the only problem. There's also the problem of, why is my system leaking? And where is that noise coming from? And why hasn't the equipment arrived yet? And what idiot broke it last night when I had already left the lab? Those are other key problems of experimental physics. But all of those problems just make it harder to answer this problem of how high are the peaks. Now let's go from characterizing this qualitatively to quantitatively. What we would say if we were to just look at one line here is that this line has the form I of lambda minus lambda 1, where I is called the instrument response function. All right, I of lambda minus lambda 1 is the instrument response function. For any instrument you're ever going to work with, you want to characterize its response function, which is just simply a function that tells you, if I send in a pure input, how much is my output spread out, okay? And instrument response functions tend to look something like this. Most decent instrument response functions tend to look like this, and they're often approximated as either a Gaussian e to the minus, if we call this axis lambda, lambda squared over w squared, where w is a width, or 1 over 1 plus lambda squared over W squared. They tend to approximate them as either Gaussian or Lorentzian, or sometimes other things, but those would be the most common approximations if they're more or less symmetric. They don't have to be symmetric. They can be asymmetric, but if they're roughly symmetric, then these are the things that they get approximated with most frequently. And there are other approximations you can make. My most cited article is a review article on techniques for fitting different approximate instrument response functions to two-dimensional data. This is how things work. Then in the case of the pure input, we can write it as, output equals I of lambda minus lambda 1 equals the integral, all right here, the integral over the full range of our data of our source of lambda prime times our instrument response function of lambda minus lambda prime. And since this is a delta function of lambda minus lambda 1, when you integrate a delta function multiplied by some other function, you just get the value of that other function when your variable is, when the input to your delta function is 0. So this has to be the value of I of lambda minus lambda 1 when of lambda prime, excuse me, lambda minus lambda prime when, and that should have been lambda prime, my bad. And so we would be left with, this is the value of lambda minus lambda prime when the input to the delta function is 0. Now, if you're getting confused by all of these differences of variables when we have delta functions, don't worry, we're about to go beyond that. We're about to go to something that's actually simpler. And likewise, if we have two inputs, our source is A1 delta of lambda minus lambda 1 plus A2 delta of lambda minus lambda 2. The A's are just telling us the how much question. Maybe sending in more light of one frequency than another, more molecules with one mass rather than another. That's all that's telling you. And then the integral of S of lambda prime, I of minus lambda prime, that's our output. And the way to think about this integral is for each value of lambda prime, for each possible wavelength, we see, okay, how much source is there at that value lambda prime? However much source is at lambda prime, our response will be I of lambda minus lambda prime. Because remember, you may be thinking, but there's no actual source at anything other than this wavelength. Well, yeah, there's no actual source, say, over here, but our output acts as though there's a source here. You may be saying, no, our output is acting as though there's a source over there that just kind of spills over. Well, sure, if you measure the whole peak, then you look at it and say, yeah, there's actually something over here, and we'll pretend that I drew it with the peak actually right there. There's actually something here, and this was some spillover. If I look at the whole thing and I analyze it, then I get to say that. But that's after I've done the work. Before I do that, if all I say is, hey, what did my instrument spit out right here? Well, my instrument spit out something here. And it spit out as though there was something at other wavelengths spilling over. So you're summing over all of the different wavelengths and how much would spill over from another wavelength to here. If I want to know how much I get here, I have to ask how much was here and how much of that would spill over, how much was here and how much of that would spill over, how much was there and how much of that would spill over, and every other wavelength. At each wavelength, I have to say how much is there, how much is at my other wavelength, i.e. lambda prime, how much would spill over. Make sense? Ask some questions.
I'm just trying to make sure my notes are on par with yours. So where it says equal to the value of I as a
Where
function.
what says equal, what? What are you talking about?
Right in the middle of the page on the right-hand side, it says value of I, lambda minus lambda something. If you scroll down a little bit.
Oh, if I integrate something multiplied by a delta function, whenever I integrate something multiplied by a delta function, I get the value of that something when I plug in whatever would make the input to the delta function 0. Basically, I get the value of that function at the spike of the delta function.
Okay. Okay.
Other questions? So what I've got here is I've got something called a convolution integral. All right. A convolution integral is just a way of multiplying two functions together. And they use this notation. I'm going to from now on write just output equals input convolved with response. And the notation for this is S star I, where S is our source, I is our instrument response. And this star is supposed to be larger than the star you would use for a complex conjugate and at a different height. And we're just supposed to not confuse it with a complex conjugate. This is one of those things that all the books do. I've been griping about the O notation. That's unique to this book, but every book that I know of refers to convolutions with a star. So this is not some unique oddity of one author. This is what everyone does. So in general, the convolution of two functions, f and g, can be written like this. F of x prime, g of x minus, now let me make sure I'm not getting a minus sign wrong. Okay, yeah, that's right. G of x minus x prime dx prime. And this is something that the electrical engineers are actually better at than the physicists. Electrical engineers take more classes on this than physicists. Physicists tend to just kind of learn this on their own as they do experimental work or sometimes theoretical work. If you really want to learn this, you get some books on signal processing that are written by and for electrical engineers, and you study those. Well, let's do some properties of convolutions. It turns out that F convolved with G equals G convolved with F, which is good because it means that we don't have to be too nitpicky about the order of things when we do convolutions. And here's how I'll prove that. G convolved with F, by the definition that we wrote up there, would be integral from minus infinity to infinity of G of X prime, F of X minus X prime, dx prime. Now let's do a U substitution. U equals X minus X prime. So then du is minus dx prime. And X prime would be X minus U. And then note that when X prime equals minus infinity, U will be equal to X minus negative infinity or X plus infinity. And if X prime equals plus infinity, U will be equal to X minus infinity or minus infinity. So when we put all this together, we've got a minus sign because dx prime is minus du. So I've got minus the integral from plus infinity, because we read those bounds, plus infinity to minus infinity of G of, where was it? G of X prime becomes G of X minus U, F of U du. And I can take that minus sign and switch the limits of integration back. I'm left with integral from minus infinity to infinity of F of U, G of X minus U du, which is exactly the same as the convolution of F and G, done in the other order. And you may be thinking, but wait, one of those integrals was in terms of U, and the other one was in terms of X prime. But, you know, as I've said a million times, that which we call X minus, that which we call X prime would by any other name still get integrated out. It's just a name change. It's not a change to anything that actually affects the answer. What questions do you have?
So this might be a really stupid question, but how it says F star G, does that just mean complex variable, or are they multiplying?
No, that star is the notation for a convolution.
Okay, gotcha.
All right, the star winds up having multiple usages. And like I said, I'm willing to deviate from the book's notation in those cases where the book is using notation that other people don't. But I'm not the idiot who decided that convolutions will be denoted with stars. As far as I was concerned, superscript star should be complex conjugate. Star on the regular level should be multiplication. You should come up with something else for convolution. But every other book out there decided this. And I don't usually deviate from unanimous notation. Other questions? Another property is that convolution is distributive. So F star G plus H is equal to F star G plus F star H, or F convolved with G plus F convolved with H. You could see that just by writing down the integral. You would get F of X prime times G of X minus X prime plus H of X minus X prime X prime. Any questions at all on what convolutions mean?
I was actually just going to ask that.
What about it?
Like, so how do we know when something's convoluted?
Well, if the integral winds up looking like this, then that's a convolution. If you wind up having an integral that looks like this, that's a convolution. The way to think about why experimental output is usually a convolution is that you ask, how much signal does my device give me at a particular value of lambda? Well, it winds up giving me a signal that on how much input was at each of the other lambda values multiplied by some function that tells me how much spillover there is. And so you could say that output equals sum over all possible inputs of input times spillover. And that's going to be the input will be some function of x multiplied by some function, sorry, x prime, because if output is at x, x prime is going to be how much, sorry, f of x prime would be how much input at x, and g of x minus x prime is the amount of spillover from x prime to x. So one of the functions in our integral just depends on our variable of integration, x prime, and the other one depends on x minus x prime. How far our measurement, how far the point we're measuring at is from the point we're currently looking at.
And so like the use of this would be to know like how accurate your research is.
That's a very crude way of saying it, but yeah, it's about how good, how accurate your research is depends on the entire process of your research. To know, it's a way of modeling how wide your data is, okay? If you had an absolutely pure input, you would get this spread of output, and you use a convolution integral to model that process, getting a spread of output from a pure input, or more generally, getting a spread of output from a spread of input. Because what if our input well, we'll just keep calling this lambda, all right? And I'll say this is our input. Now, each piece of this input gets spread out a little bit, okay? Each piece of it gets spread out, and then it gets spread out by different amounts. And so I'm adding up all of these spread out functions. When I add up all of these spread out functions, what do I get? I get something that's a little bit broader here, and it's a little more spread out in there. So the dip is much less noticeable, and then it's more spread out there. So what I get reflects the fact that every point on here, there was a spread, okay? My output is a spread out version of my input. Just by adding up a bunch of these spread out functions, and the height of each spread out function depends on my input. Because if I have a very high input here, well, then I take a very big thing and spread it out. If I have a low input here, I take a very small thing and spread it out. Question in the chat, isn't this trying to figure out what is the interference in the experiment? Well, the word interference has a very general, broad meaning and a very specific meaning. The very specific meaning of interference is waves with different phases acting up and possibly canceling or possibly reinforcing. But interference can also just mean something else getting added into your signal and messing it up. So yes, in that sense, it could be interference, but we should be very careful with terminology here, because in an optics experiment, waves of different frequencies, waves with different phases adding up and either reinforcing or canceling could be exactly what you're looking for. It might not be some spurious thing you want to eliminate. It might be the very essence of the phenomenon you're studying. On the other hand, waves from something other than your experimental apparatus or your sample that you're looking at could be quite the opposite. Like, what if you are trying to do a fluorescence? Okay, what if you're trying to look at autofluorescence from a patient's skin to see if they have skin cancer? This is a very active area of research, using nonlinear microscopes to diagnose skin cancer. Okay, any light coming from the skin, totally signal, totally something that you want. Any light coming from the room, totally spurious, totally something that you don't want. Both of them could be causing interference when they go into the microscope. The microscope is using certain kinds of phase masks in order to achieve some interference effects. So I don't like using the word interference here, because it winds up meaning two different things. Other questions?
If we have time, can we see an example using this?
I put some convolution integrals on the practice assignment. Doing a convolution integrals are almost always very hard to do, which is why they're either done via a trick that I'm about to show you, or they are done numerically. You just write a computer program to do them. People rarely sit down and do some convolution integrals. I sat down the other week and tried to do some convolution integrals. And for one simple integral, I found myself doing 3 pages of algebra and decided that I won't put it onto an assignment. But again, so the actual, if you mean see an example doing the actual integral on paper, if I give you what you asked for, you will curse me. So I'm not going to give you what you asked for there. If you mean an example, I mean, I'll do something graphically, kind of like what I was already doing. By the way, I very much believe in giving people what they ask for. You could say that that is my entire approach to academic politics, not to be confused with real world politics. Suppose that the actual spectrum of something was a line here, and a line there, and a line there, and a line there, okay? And there may be reasons why something has 4 very closely spaced lines, but the instrument response is this wide, all right? So I replace this line with something that's wider. Then I add to it something wide there, and something wide centered there, and something wide centered there. And when I add all of these up, I'm going to get 1, 2, 3.5, so 4, 5, 6, 7, a height of 7 there, and I'm going to get a height of a half. So I'm going to get a half, this is about a half there, so about a half higher. So I take the half here and I add it to whatever was there. I go up a half. Over here, I've got 1, 2, 3.5. So I go up to there. Over here, I've got this height plus a half and another half. So I go up to there. So I can wind up getting a spectrum that looks like that. Good luck deducing the underlying structure from this data. You've got data that looks like this. Good luck deducing the actual underlying structure of these 4 lines from something that looks like this. The only thing you could really do is you could look at this and say, you know what? There's more than one line there. That's the only honest statement you could make. You could say there's at least two, but maybe there's some finer structure.
Dr. Small.
Yes?
So, okay, so the two graphs that you have here, the very first one where you've added up all those amplitudes, that's the combination of raw signals, correct?
Yeah, that's showing the actual things that came into the instrument. If I could somehow know this in reality.
Right. What about below that? What does that represent?
That is the instrument response function, okay?
Got it.
Anything else? Okay, then let me prove something called the convolution theorem, because the convolution theorem is what we will use to actually do these integrals. It looks more abstract, but believe me, it's better than the 3 pages of algebra that I got when I tried to do these by hand. I want you to do these in Wolfram just to see what the results will be. That's what's on your practice assignment. Let's say that C of x is equal to the convolution of F1 and F2. We could Fourier transform these two. Let's ask, what is the Fourier transform of C? Oh, let's see, C of x was the integral from minus infinity to infinity of F1 of x prime times F2 of x minus x prime dx prime. Whoa, I hear those Santa Ana winds blowing so hard. Actually, my house shaking a few minutes ago from the Santa Anas, but now they're actually louder.
That's
Okay, so the Fourier transform will be the integral over x of e to the minus I kx c of x dx, or the integral from x equals minus infinity to infinity, and the integral from x prime equals minus infinity to infinity, e to the minus I kx f1 of x prime f2 of x minus x prime dx dx prime. Damn, those winds are freaky. I don't know if you guys can hear the Santa Anas, but they are howling almost like a train or something.
I thought those were ambulances running up and down your street.
It was a ghost.
No, they're definitely not sirens. Yeah, okay. Well, I'm pretty sure that what the haze I saw over the mountains has been blown away now. Soon to be replaced by smoke from the fires that will quickly start by the Santa Anas. Ghost of physics past. All right, so now let's do a U substitution in here. Let's say that U is equal to x minus x prime. Then when we hold x prime constant, when we integrate over x, during the integral over x, we hold x prime constant. So du is just equal to dx, and x is equal to u plus x prime. So what this means is that we can write, we're gonna get rid of that and then go back to my pen. I can rewrite this as the integral from minus infinity from from u equals minus infinity to u equals infinity, and the integral from x prime equals minus infinity to infinity of e to the minus I times u plus x prime f1 of x prime f2 of u du dx prime. Or I can factor this and I get e to the minus iu, e to the minus, oh, and there should be a k in there. So I can rewrite this as an integral from u equals minus infinity to infinity of e to the minus I k u f2 of u du, integral from x prime equals minus infinity to infinity e to the minus I k x prime f1 of x prime dx prime. Or a1 of k, a2 of k. The Fourier transform of f1 multiplied by the Fourier transform of f2. So the Fourier transform of two functions convolved equals product of the individual Fourier transforms. So if I can, not if I multiply two functions, if I multiply two functions, the Fourier transform of the product is not the product of the Fourier transforms, but if I convolve them, if I do this integral, then the Fourier transform of the convolution is the product of the individual Fourier transforms. Any questions on the process before I start talking about the implications of this for experiments? Okay, well, the first consequence is that your output always has a narrower frequency range than your input. Here's why. Let's say that I'm going to pretend that I'm going to say that S of k is the Fourier transform of our source. And I'm going to say that H of k is the Fourier transform of our instrument response, because that's a more common notation than I of k. Capital I is almost always an intensity. And I can always choose my units so that the peak of each of these is 1. All right, and I'll do H in red. I can always choose my units so that the peak of each of these is 1. Or if you prefer, I can factor out a constant and then bring that constant back in the end. Won't really matter. So at the peak, if I've designed everything right, then the Fourier transform of my instrument response function has its peak at the same, say, spatial frequency, if I'm doing some imaging, it has its peak at the same spatial frequency as the Fourier transform of my data. That's just another way, or the Fourier transform of my input. That's just another way to say that I've designed my experiment very well. I've designed my experiment so that my instrument has its maximum sensitivity at the input, at the peak of the input. And for instance, the human eye's instrument response function actually is actually calibrated to the sun, all right? If you think about where is the peak of the solar spectrum at the ground, and you think about where is the peak sensitivity of the human eye, what is the wavelength where the human eye has its maximum sensitivity? The human eye's maximum sensitivity is in the green. Of the solar spectrum at the ground is roughly yellowish, pretty close to green. And the reason why we're not exactly at the peak, I mean, there's a whole bunch of biochemical and evolutionary reasons for that, but they're pretty close, all things considered. So now I've got two functions whose peaks are 1, and their product is always going to be even lower. All right, so if I draw their product, all right, if I draw their product, then their product is going to be lower everywhere, and the result is a function that is narrower everywhere, right? So unless your instrument has a very, very wide, flat response function, unless it has a perfectly flat response function, your output will cover a narrower range of frequencies than your input, which means information loss is assured. So experimentalists spend a lot of time dealing with their instrument response functions. As a matter of fact, if you look at equipment manufacturers, they will often include instrument response functions, sometimes Fourier transforms of instrument response functions with their technical notes, with their manuals and specs. They will include Fourier transforms of instrument response functions, because that's how people think about these things. That's what people need to know. That's what tells you about information loss. Now, one thing that someone might say is that if our output at a frequency k is equal to signal at k, or I'll write input at k multiplied by h of k, the response function, someone might say in the voice of Eric Idle near the end of Monty Python and the Holy Grail, hey, I've got a great idea. Why don't we just divide these? So we get our input of k is equal to the output of k divided by h of k, which sounds great. Can anyone see a problem with this? H of k is going to 0, far away from the peak. Now, that's not necessarily a problem. That doesn't have to be a problem. If S of k is also going to 0, well then, hey, we got nothing to worry about, because S of k you would hope that S of k would also go to 0. And if we had a clean signal, if we have a clean signal, then S of k goes to 0 as well. But away from the peak, we get noise. And even worse, if I were to actually look at pixelated data, right? If I were to look at data with finite bin sizes, then here's my ideal. Here's what I actually get. I get a bunch of noise on top of it. And you see how the noise is jittery? See how there's fine details in that noise? It's jittery. The noise going from one channel to the next one, a channel just being a point that you could detect that. The noise going from one to the next jitters up and down. Well, if I've got a function that jitters up and down on small scales, you tell me, does that function have a high frequency or a low frequency?
High frequency.
High frequency, very short spacing between peaks. I've got high frequency noise. So output over h of k is equal to ideal output plus noise. There's the output from the instrument responding to the true signal. The true signal, the real stuff is going in. Whatever I'm actually trying to measure is going in, okay? But noise is also going in. And the ideal over h of k, this is well behaved. If that was the only thing I had to deal with, this would be easy. But we've got noise divided by h of k. And the noise is non-zero at high frequencies, and h of k is going towards 0 at high frequencies. So we have a division by 0 problem. And most scientists, this is the final thing I'll say because we're out of time, most scientists, they think they're going into their career to study biophysics or solid state physics or astrophysics or particle physics or whatever. And then they spend a whole bunch of time trying to clean out noise from their signal, all right, and purify it. And so a lot of scientists wind up sort of becoming, I don't want to say amateur because that disrespects what they're doing, but they don't take a lot of formal courses on signal processing and statistics, but they wind up learning a lot of this stuff via various informal and sometimes formal mechanisms. And so they acquire a very broad education, but piecemeal on signal processing and statistics. And I would encourage all of you, whether you think you're going to industry or you think you're going on to the academic basic research grad school track, to take some statistics classes, to take some signal processing. If you look at the catalog and it says to take EC, whatever, you need a bunch of prereqs, just go to them and say you're a physics major with good grades in your math and math methods courses, and maybe they'll let you in. Maybe they won't, but try to learn some of that stuff. That is so useful in industry where you're trying to clean out noise from signals. It's so useful in academic research where you think you're going in to say, hey, I want to study fundamental questions in superconductivity or supernovas or super resolution microscopy, to pick from 3 very different branches of physics. And instead you wind up doing a bunch of signal processing. We're going to talk more about this on Wednesday, and then we're going to go into Fourier transforms and optics. I'll stick around for a few minutes if people have questions. Otherwise, have a good day.
Thank you, Dr. Small.
You're welcome.
Yep.
Thank you.
Dr. Small.
Mhm.
Did your economics background help you with the statistics? Is that kind of what you're referring to?
It did. I took a bunch of stats classes taught by econ professors, and I enjoyed it very much.
Okay.
Of course, I learned even more statistics after that. You never stop learning statistics. But
Mhm.
yes, it helped.
Okay, perfect. Thank you. Have a good day.
You too.
Hey, Professor,
Yeah.
I had a question about the practice assignment 9, the second integral.
Yes.
It's changed now, so I did it again. Are we supposed to assume that x is also, just the regular x is also real? Because if we don't, then we get a different answer.
Yeah. Assume everything's real.
Thank you. And one more thing.
Yeah.
The Fourier transform is distributive over addition, right?
Yes.
Does that go, is that the same thing with the
Convolution.
Fourier series?
Yeah.
Or-
If I add up two periodic functions, the Fourier series of the sum is the sum of the individual Fourier series.
That seems to conflict with my the number, the last one on our homework assignment 9. If
Oh.
you take the individual Fourier series and add them, you end up getting the same function, which is kind of weird when it's non-periodic.
Okay. The sum of two Fourier series is another Fourier series if each of those Fourier series has the same period, has the same fundamental period.
So why does it work that if you take is that just pure coincidence that if you take the Fourier series of, like, say, sine of x and then take the Fourier series of sine pi x, you end up getting sine x plus sine pi x?
Well, the Fourier series of sine x is just sine x. So an individual trig function, the Fourier series is pretty trivial. We're dealing with a trivial case. I think the question I really wanted to get at was, if I just add up two periodic functions, do I automatically get another periodic function? And the answer is no.
That's only if one of the functions has a frequency that's not undefined. What's it called?
If they have the same fundamental frequency. If one of the frequencies is an integer multiple of the other, then it can work, because then they
Okay.
ultimately have the same fundamental frequency.
All right, thank you, Professor.
You're welcome. Anyone else?
Yeah. So next semester I plan to take classical and E&M, and someone actually told me to ask you about that. Do you think that's possible? I'm doing pretty well in your class, I'd say. I have a A-, I think.
Oh yeah, then if you're doing well with the math, I mean, classical and E&M is hard, but it's not impossible. It depends on how good your math is. And if you're doing pretty
Okay.
good with math, then yeah.
What if I'm also taking astrophysics with that?
Then I guess I would say that if you're gonna do those three classes, fine. If you're gonna take a fourth class, make sure the fourth class is easy.
Okay. So don't do chemistry with those classes.
That depends on whether or not you consider chemistry an easy class.
It's not hard, it's just a lot of memory, and I know that. But okay, yeah, you're right.
Yeah, I mean, look, I think the standard, to me as a physicist, I hated chemistry. So
Yeah.
later on in grad school, I wound up doing a ton of chemistry. I hated freshman chem. I found it very difficult. So for me, I would not do that. Now, some people actually really like chemistry. If you're looking at chemistry just going kind of no, then yeah, you're right. Don't take chemistry with it.
Got you. Okay. Yeah, it's super off-putting to me because, like,